Hello everyone, and welcome to video number 5 of this series, in which we are learning how to model an end plate steel connection, which is this model that you see here. In the previous videos, we have defined the geometry, that is the domain of the mathematical model, and we also have discretized this domain, which means that we have divided into elements, the finite elements. And we know that discretizing the domain is one of the first steps of the finite element method solution procedure. Well, in this video, we are going to start creating the bolted connections that we are going to have here. But before we start, in the draw mode, you can change the draw mode by clicking here. Guarantee that you have PID selected, so the parts are going to be painted as per their PID. And also in these yellow buttons, guarantee that you have the same buttons activated here. This is related to visualization of cones and points. In the perimeter points, deactivate the visualization of spots. We don't need to see spots. I know that I didn't explain to you about spots, but this is not really important for this tutorial. And also, one thing that I forgot to mention in the previous videos is that you see that we have this deck here, this module here that is named as decks, right? If we click on this drop-down list, we have many solver options to choose, right? Depending on the solver that we choose here, we are going to have a different structure in the database. And this is something that is important for me to explain, because in the previous videos, I have shown the database to you many times. And maybe if you had another solver selected here, you would see something a little different. For example, notice that when I have Abaqus selected here, which is the case, node is named as node, this first item. Now, if I choose here Nastran, then node is named as grid. Okay, it's just a different way to name some entities. So, well, if in the previous videos, when I presented the database, if in your case you had something different, then that's the reason. Well, another thing that I needed to mention here is in quality criteria. So let's open the quality criteria. And if you have just opened ANSA, if today is another day for you, you're going to notice that the quality criteria are not set up anymore. Even though you opened the .ANSA file, before closing it, you have set up the quality criteria. So when you open this .ANSA file again, you're going to notice that the quality criteria are not set up anymore. So that's why it's important to save the .ANSA qual file that has the information of the quality criteria that you have used previously. Okay, so if you saved this file, the .ANSA qual file, then click here in this folder and then search for this file. And then you're going to have the quality criteria ready to go. But if you didn't save the quality criteria file, just pause the video and copy what I have here. And then click on apply, and also save this file this time. And then click on OK. Well, we're not going to work on the mesh anymore because we have finished, but it's important to have the quality criteria set up, because maybe we need to modify some things in the mesh. All right, so the next step here is to, we're going to use a different module in this video. we are going to use the DEX module, and then click on this drop-down list and select Abaqus, which is going to be the solver of this mathematical module. Well, I have mentioned previously that this first module is going to be a little simpler because we are going to model the bolted connections using a coupling here on the end plate, another coupling here on the flange of the column, and then we are going to connect the couplings through a beam element. Okay, this is a simple way to represent a bolted connection. It's used a lot in the industry. But when we want to have more valid results around this region, then we need to consider solid elements to represent the bolts. We need to create a more realistic representation. Okay. All right. So let's start. Now in the Abaqus deck module, we are going to have these new tools, and then you see that we have the constraints group, and then in the constraints group we have coupling. By the way, I have a blog article that I talk about couplings. I talk about distributing coupling, kinematic coupling. If you're interested, I'm going to let the link to this blog article in the description of this video. Let me just write it down here so that I don't forget. Coupling article, link, description, just so I don't forget to put this link there. But anyways, I'm going to give you an overview of how this works when we create it. So left click in coupling and hold until you see these options. And we have many ways to create it. We are going to create it by selecting nodes. So release the left mouse button when you have the mouse positioned here. And now we have this new window, coupling nodes. Now we need to select the surface nodes. We can select by nodes, by edges, by elements. We're going to select by nodes. Zoom in one of these holes and then select the entity selection mode. And then when we do this, we need to select one node, one single node per click. And this is not really so efficient, right? So instead of doing this, I'm going to deselect everything using the right mouse button. And then I have some selection tools here. And one that is going to be important in this case is this one here, loop. If I click on this drop-down list, I have loop and opposite. We are going to use loop. Now loop is activated. If I position the mouse here, you see that the software is going to recognize a loop of nodes. And then if I left click, I have all these nodes selected in one click. Now, if I position the mouse on this loop, I can select this other loop of nodes. And I want to select only 2 loops of nodes. Now you understand one of the reasons why we created these washers around the holes, so that we have this more organized pattern to select the nodes for the coupling. So after selecting these nodes, we can click on next. You see that we have 52 nodes selected. Click on next. And then we need to select the control node. The software automatically calculates the control node on the convex hole centroid, which means that it creates this control node on the COG of the selected nodes. And in this case, this is exactly what I want. Okay, so simply click on next or use the middle mouse button, and then you see that it has created this control node here, and it has connected this control node to the surface nodes that we have selected previously. So these are the slave nodes of this coupling. These two loops of nodes are the slave nodes, and then we have the reference node in the center. We know that a coupling works like, well, an intuitive manner to think about a coupling is that everything that happens to the reference node is going to be distributed to the slave nodes. So if I apply a force here, this force is going to be distributed between the selected nodes here in the surface nodes tab, or not tab, but these slave nodes. So that's how this works. And then you see that in type, we have two main types, distributing and kinematic. These are the two options we never use. This kinematic coupling is not even compatible anymore with the current versions of Abaqus. So what matters here is distributing and kinematic. An intuitive manner to think about kinematic is that when we have it selected, the nodes that are selected here as slave nodes are going to be rigid. Not the nodes itself, but the elements that contains these nodes are going to be rigid. Basically, this means that the relative position of these nodes is not going to change. You see, for example, we have this node and this node. We have this relative position between them. And this relative position is not going to change anymore if we choose kinematic. Okay, so these elements here are going to be rigid. When we choose distributing, then these elements are going to be flexible. They are going to deform. So the relative position can change. Okay, so that's the difference between distributing and kinematic. I prefer to use kinematic most of the time because kinematic facilitates convergence of the model in this region. But you should know that if you are working in a big company, when you get to create a model, you will need to probably follow a procedure that is established through a document. For example, I worked at Stellantis, and when I needed to create a model, I would need to follow something named as standard operational procedure. And then in this file, I had that, well, you should create the bolted connections using coupling, beam coupling, and the coupling should be kinematic or distributing, and etc. So I would have all the orientations because they have tested before this modeling strategy, and they know that this works. And then if I use this strategy modeling strategy, then my model is validated already. Okay, so this is how it works. Depending on the situation, we use distributing. Depending, and in other situations, we use kinematic. It really, it really depends on what happens in this connection. For example, one reason to use kinematic is because in this region, we are going to have the washer of the bolt contacting, right? So if we have a bolt pretension, there is going to be a pressure between the washer and this surface, right? And when we have this pressure, this surface is more restricted to deform. And then to represent better this situation through this coupling, we use kinematic. So you see there are some reasonings and The thing is that to really validate, you should create a more detailed model, and this one that is more simplified, and then test kinematic, test distributing, check the stress around this region, and see what option represents better. But again, I prefer to use kinematic most of the time, because when I use this bolt modeling strategy, I'm not interested in the stress around this region. So that I simplify this bolted connection. If I'm interested in the stress around this region, then I would use a more detailed bolted connection modeling. That is, I would use solid elements here for the bolt, washer, and nut. Another thing that I need to highlight, yet related to these orientations, you see, let me finish the creation of this coupling before this explanation. Let's choose then kinematic, and then you see that we can select the degrees of freedom that we are going to create the relationship between the reference node and the slave nodes. Most of the time, I simply select all degrees of freedom. And in here in part, let's select ask always, so that when I click on finish, the software is going to ask what part I want to assign this new entity that has been created, which is the coupling. Let's create a new part by clicking here, and let's name this as connections, or connection underline entities, something like this. And then double click on this new part and close this, and now we have this new coupling created. If we go to the database, we have this new item named constraint. Maximize it, and we have this new item here, coupling. Double click, and then we can access the coupling here. If we double click on it, this card is going to pop up, and in here we have the information of the reference node ID and the slave nodes. So we have this list here. The kind we can change here if we'd like to, the degrees of freedom, and etc. So let me close these, and now let me explain another thing. When we created these washers, for this diameter of this loop of nodes, we didn't establish a specific value for this diameter, right? But in reality, in this file that has the orientations that you should follow, sometimes we are going to have an orientation like this. You should define this diameter to be the same diameter of the washer that we would have here. I mean, the washer that we would have here would have an internal diameter and an external diameter. Then this diameter here should be equal to the external diameter of the washer. Okay? Sometimes we have orientations like this. But in this case, we have just created with an arbitrary diameter. But you should have this in mind. All right. So now let's create a coupling here on this other face. Activate coupling, simply left click here, and then select by nodes. I'm going to teach you now another way to select these. If I click here, I'm going to activate a selection mode based on elements. So for example, if I select this element and click on middle mouse button, the software is going to select all nodes of this element. So we are yet selecting nodes, but we are selecting it through elements, right? So in this selection mode, I want to use this option here. If I click on this drop down list, I want to select poly area. And then you see that if I select, for example, this element with the left mouse button, And then this one, it's going to create this path between these 2 points. Now, if I select this one here, then it's going to create this loop. And then if I click on middle mouse button, it's going to select all these elements, and middle mouse button again is going to select all these nodes that are part of the selected elements. I usually prefer to do this in this manner. Now we can click on next or use the middle mouse button, and then it's going to create a new node here on the COG, next, kinematic, and ask always. Finish, select connection entities, and close. Okay. All right, now the next step is to create the beam element that goes from this node to this node. But there is another kind of element that is going to be created here, and that is going to be used for bolt pretension. We are going to use a translator connector. By the way, I have a video that is only about bolt pretension, and I teach you how to create bolt pretension by using the translator connector. We're going to learn in this tutorial. But if you'd like to see this other tutorial that is only about it, then you can also check it out. But we're going to learn it here as well. Okay, I'm going to write it here to put the link to this blog article in the description, so I don't forget. All right, before let me show you how to create this beam element without the translator. Well, to do this, you see that we have this group here, element, right? And then we have this item, beam. Left click in beam, and then we have these options, select the first one. And then this appears. Let's zoom in this region, rotate a little. To rotate, use hold Ctrl and use the left mouse button. And then select this node as the first node and this node as the second node. And then middle mouse button. And by the way, you see that in here you have part ask always and property current. Let's choose here for part ask always and for property ask always as well. Middle mouse button. Oh, now it's asking select a node for orientation. We are going to assign a circular cross-section for this beam, so the orientation doesn't matter. The orientation is important when we have, for example, an eye-shaped beam or something like this, but in this case, it doesn't really matter. So I'm going to select any node in this loop to define the orientation. Could be this node. And now we need to select the part that we want to assign this beam. I'm going to select connection entities. And now we need to create a new property for this beam. We don't have any beam properties yet. Right click to create a new, and then click on new. And then we can create a name for this. If I open up the article, you're going to see that for this connection, we have the bolt diameter as 20. So let's say that this is M20. Underline bolt. And then in type, instead of general section, let's choose section. And then in section, let's choose circular. And then here we can define the radius. If the diameter is 20, the radius is 10. In here we can select the type. We can use B31, which is the Timoshenko beam element. Oh, sorry. Actually, this is not a Timoshenko. This is Euler Bernoulli. Let me just check. B31 Abaqus element. Yeah, so B31 is the Euler Bernoulli beam, and Timoshenko is B32. Okay, so Timoshenko allows shear deformation. Well, in this case, we can choose a B31 Euler Bernoulli beam, and the next thing that we need to define here is the material for this beam. Well, this part is important because we have a table with the material properties for the beam, for the bolts. It is this table here. So we have a relationship between stress and strain here. We have 1, 2, 3, 4 points. And we need to establish this here. So let's create a new material. So select this field and use the question mark to open a list of materials. We have the two previous materials that we have created, but I need to create one new material. So right click in new, and then let's name this as bolt material. The ID is going to be 3. And in elasticity, we have all these options here. For metal elasticity, we choose elastic. Well, in ANSA, we always have many options because this is a general software. So I'm going to only explain what matters. So in here we have density defined, yes, and we have a standard density for steel. Since this is a steel bolt, we can accept this density. This is in tons per cubic millimeter. And then we have elastic as yes. And then the elastic type is isotropic. Isotropic means that the mechanical properties of the material doesn't change with direction. We can define the Young's modulus. Let me see if we have this information, where we have this information. For the bolts, Young's modulus, I don't... Material properties. Well, where do we have the yields, the modulus of elasticity defined here? We actually can calculate this modulus of elasticity by using these data points. So let's do this. Let me open up Excel. So this is going to be actually interesting. Oh, actually, instead of using Excel, I'm going to use the board so I can create this drawing by using this data. So let's understand how we can tell the software about this information. If I create the stress strain curve for the bolt, this is a strain and this is a stress, right? The first point that we have here is 0, 0. So we have this point, right? The next point that we have here is 9, 9, 0. And then we have some strain. 0.483, and this is in percent. Okay, so to actually have the actual string, we would have to divide it by 100. And then we would have a straight line connecting these 2 points, like this, right? And this is the linear part of the curve, where we have elastic strain. So we can think that this is then the yield strength of the material of the bolt. We can calculate the modulus of elasticity as this divided by this. Okay, so let me do this calculation. Let me open up Excel again. So E, we have the stress, the yield strength as 990. This is in MPa, and we have strain as 0.483, but we should divide it by 100. Okay, and the modulus of elasticity is this divided by this. It is the tangent of this straight line. So it is the, well, we have this triangle, it is the opposite side divided by the adjacent side of this triangle. Okay, so this is the modulus of elasticity, and then you see that the value that we have here is just a standard value for modulus of elasticity for a structural steel. So here in ANSA, I'm going to copy this value and paste it here. Poisson's ratio, let's see if we have this information. Well, I'm pretty sure that a Poisson's ratio is not explicitly defined for the bolt, but we can assign the value of 0.3, which is a pretty standard value for structural steel. All right, now we need to also define the plasticity. And so let's continue analyzing this data that we have here. So let me use another color, and then we have this other point. So this other point is like here, 1160, and then here we have data in MPa. And then string is 13.6. So we have 13.6. This is in percentage, and we have this new point. And then in this case, we're going to have a straight line connecting these. And now we have this last point. You see that for this last point, we have the same level of stress and one additional strain. So we have 15% here and the same level of stress. So we're going to have something like this horizontal line. So we will not have a strain hardening in this region. So the idea here is that actually this curve in reality would look probably like this, right? Or the true stress, true strain would look maybe something like this, always increasing. But this guy here from this article has created this simpler, he named it as trilinear model to simplify this plastic strain versus stress curve. Okay, so instead of representing this in a complex manner, it's going to represent it by a trilinear model. Okay, this is just a simplification. that has been used. So how do we define this part of the curve in this software? So far, we have defined this part, right? Because we have defined the Young's modulus. Now to define the other parts, we should activate plastic. We are going to define plasticity. When we select yes here, we have the hardening option. And then if we click on this drop down list, we have the hardening modules to choose here. Remember that we have learned about plasticity in module 6 of the course. We have learned about yield criterion, plastic flow rule, and hardening law. And I remember that in hardening law, we have the isotropic model that when we have plastic string, the yield surface is going to expand uniformly in all directions. When we have a monotonic loading condition, which is the case that we have here, we're not going to have a cyclic loading condition. We are not going to apply like a load in the upward direction and then a load in the downward direction and perform cycles. We will not do this. We will have a monotonic loading condition. We're going to apply a load in the downward direction, for example, and that's it. And for that reason, we can use the isotropic hardening model. But if we had the condition of cyclic loading, then maybe we would have to use the kinematic hardening model, where we have a translation of the yield surface. Okay. All right. So isotropic here. And now we need to define a table with this data. So to define a table, select this field and use the question mark to open a list of tables. And well, we don't have any table defined, so we need to create a new one. Click here and data table. Give it a name. So this is the bold plastic curve, or actually, let's say that plasticity, properties, something like this. We have the ID of this curve, and then let me just increase this size a little, and also here I'm going to increase the size of this part, and we have this table. First of all, click here, Control A to select everything and delete. Let's empty this list. We have these 3 columns. I'm not going to create anything dependent on temperature, so we don't need to define anything in this column. In some cases, we can have different curves for different temperatures, and then we would need to define one curve for a specific temperature and then another curve, and etc. But this is not the case in this example. So you see that in this first column we have yield stress, and in the second column we have plastic strain. The first point that we need to represent there is this one here, where the yield stress is 990, and we have this plastic strain here. Actually, this is not plastic strain, sorry, this is elastic strain. Well, the plastic strain starts to occur here, so plastic strain starts here, which means that the plastic strain here is equal to 0. So this first point here is going to be defined as 990 and plastic strain equals 0. We should not take these into consideration. All right. Now the next point that we should define, and by the way, we are only defining this part of the curve. So the next one that we need to define is this point here. So it is 1160, and then the plastic string is going to be the difference between this and this. So let's calculate it. I'm going to put here 16 equals 16 divided by 100. Oh, sorry, it's not 16, right? It is 13.6. 13.6 divided by 100. And then I need to get this minus this. So this is the plastic string that we have here. Control C and Control V here. One important notice. Oh, let me check one thing here. 9900. Okay. One important notice here is that we should provide to Abaqus true stress versus true strain. Well, in this article, I don't have the information if this is true stress versus true strain. So let's just assume that this is true stress versus true strain, so we don't need to perform any kind of transformation. All right. Okay, so now we have defined this point. One thing that is weird in ANSA is that it plots the stress in the horizontal axis and strain in the vertical axis. We can change it. So switch to plot tab, and then in here in the axis data, in X plot 2 and in Y plot 1. And then we end up having stress in the vertical axis and strain in the horizontal axis. Okay, so here we have this point here, 990 and 0. And then this point here is 1160 and 0.13. Now to create one additional row, select these and press enter. And then the next one is, the stress is 1160 and the strain is 15. So it is 15 divided by 100, and we have 0.15, and then we should get these and subtract by the elastic strain that we have. And then let's copy this value here, and now we have this horizontal line, which means that the bolt has lost its stiffness. We have an increase of strain without any increase of stress. Not the bolt, but the specific material point that we have inside this bolt that has this condition has lost its stiffness. All right, so that's all we need to define here. We can click on OK, and now we have this table to select, double click on it, and you see that it puts here the ID of the table that we created. We can access this table by selecting these and pressing F2, and here we have the table again. Click on OK, and yeah, that's it. That's all we need to do here. And just one additional comment. We have learned about, in this module, we have learned about these 3 items, right? The yield criterion that is used in Abaqus is the von Mises yield criterion automatically when we have this setup, when we have an isotropic material and with isotropic hardening. And the plastic flow rule that establishes the relationship between stress and plastic strain for a triaxial stress state is we don't need to select it manually. It is selected automatically. And the plastic flow rule is directly related to this one that we have learned here. Let me select here, which is the printed Roy's equations for elastoplastic solid. Okay, so this is selected automatically based on the previous configurations that we have defined here. Okay. All right, so we are finished with this definition of plasticity. Now we can click on OK, and we have this material to select. Double click on it, and now we have the ID of the material selected in the definition of the property that we are creating for the bolt, for the beam element that is going to represent the bolt. So in the card of this beam, we have the ID of this property. We have defined here section, circular radius of this section equals 10, the properties of the material, and the type as B31, that is Euler-Bernoulli beam. Click on OK and select this property from this list, double click. And now we have the card of the beam itself, B31. Where we have the property selected for this beam, we have the beam ID, we have the ID of node 1, which is the ID of this node, the ID of node 2, which is the ID of this node, and we have the orientation procedure that doesn't really matter for a circular cross-section beam. Click on OK and close this. If we zoom in here, you're going to see that we have this new entity, which is the beam element. We are going to have a new item here in the database named beam. Double click, and we can select this beam, and it's in this list. We can access it by double clicking here, and then we have the card of the beam. If we want to access the property that we have created, select this and press F2, and then here we have the property. If we want to access the material that we have created, select this field and press F2. Here you have the material, and so on. You're going to get used over time how to deal with these cards. Okay, you see we have the plastic, the table, press F2, and here we have the table. And then click on OK, OK, and OK, and OK, and etc. For us to check if everything is alright, we can visualize the section of this beam. To do this, click on Quality Criteria, Presentation Parameters, and then there is this option, Line Elements, Activate, and Draw Mode as Shells, Apply. And then you see that we can visualize the beam section. And looks like it's okay. Looks like it's correct. The diameter. The diameter is a little smaller than the diameter of the hole. We have defined this diameter of the hole as 22, right? And the diameter of the beam is 20. So this looks correct. Let me deactivate this and click on Apply and OK. All right. Now, let me show you a very nice tool to create this kind of connection in a more automated manner. When I create this kind of connection, I don't do this in this manner. I have shown to you how to do this in this manner, so you learn how to create a coupling, manually, a beam element, and etc. But in reality, what I do is, well, I use this tool here, Bolt. It is in this region. If you don't find it, just search for it in here. Or also, if it's not visible here, you can click on this arrow to see more options. And then activate Bolt. And then we have this window. And then in selection, let's select by nodes. And then the body of this bolt is going to be beam. And we can choose many options here, but it's going to be beam. And the head of the bolt, you can think that the head is what is going to be on this side. And then you see that we have nut. Nut is going to be what we have on these sides. Okay, so the head is going to be coupling because I want the software to create something like this, a coupling. And the nut is going to be coupling as well. So it's going to create a coupling on this side. Now, let's use, to select the nodes, let's activate this tool here to select elements, and then let's activate the poly area selection mode. Zoom in here, select this element, another in this loop, and another in this loop. Once you have selected 3, it recognizes that it should select this whole loop of elements, middle mouse button again. Now you see that it has selected all these nodes. Now let's go to the other side. To rotate, hold Control key and use left mouse button. Left click on this one, and this one. Middle mouse button, and then middle mouse button again. Now you see that it has selected all these nodes. And it has created this red entity, which is going to be the beam. Now, middle mouse button, and in here, first of all, we need to select the PID that we want to assign to the beam that is going to be created here. So select this field, question mark, and select this property that we have created. Now, the diameter is 20, and coupling head should be a kinematic, and also coupling nut, kinematic. We should have activated all degrees of freedom, and that's all we need to do. Click on OK. Now we need to select the part that we want to assign these entities. Select connection entities. And you see that this software has created, let me close this. The software has created one coupling on this side, another coupling on this side, and this beam element between these nodes. Okay, well, I guess I'm going to do something different here. Let's run this first model without bolt pretension. It's going to be just a first test. And then after doing that, we are going to modify this and insert a translator connector so that we can apply bolt pretension. I'm going to do this in this manner because I don't want to. I don't want you to get confused. I want you to firstly see how it works in this manner. And by the way, this modeling strategy without the translator, that is without applying bolt pretension, is very common. Okay, it is used a lot. So let's firstly do this in this manner. So let's create these connections for the other bolts. Again, activate bolts, and you're going to see how practical this is. Select nodes here, and then you see that we have everything set up correctly. And then I have the selection mode already correct as well. And then select 3 elements in this loop, middle mouse button again. Now rotate, and then select 3 elements in this loop, middle mouse button twice, and middle mouse button again. You see that we have everything correct here. The diameter is not correct, but you're going to see that it doesn't really matter the value that we use here, because the diameter is defined in the PID. So what matters is that the PID is selected correctly. Here we have the ID of the PID that we have created. So everything is correct. Click on OK and select the part. And that's it. The connection is created. Let me close here, and let me show you one thing. You see this beam that has been created. If we double click on beam in the database and select this beam, double click here on this item, and then we have the card of the beam, and it's just to show you that everything is correct. So we have the PID F2 here, and we have this property assigned with this radius. Okay, so that diameter field doesn't really make any difference. What matters is the PID. All right, so activate bolt. Select 3 elements in this loop, middle mouse button twice, 3 elements in this loop, then middle mouse button twice, and then middle mouse button again and again. Select this part, and then go to the next hole, and let's do this faster now because I think you understood well about it. Okay, there is just these two. All right, we are finished. Now we are finished. Let me close this, and let me just check one thing here. I want to check if in the model browser, activate model browser, and I have this part. If I right click on this and show only, you see that I have some couplings and beams that are not in this part. And the reason for that is because when I created some entities, I forgot to select something here. I just clicked the middle mouse button, and this ended up going to the to another part. So what I'm going to do here is, if this happens in your case, I'm going to show. I'm going to use this button with this visible, which is the entities of that specific part that we have isolated. I'm going to click on this button, invert. So it's going to show the other parts that was not visible. And then I'm going to use this tool here, not. Not is to hide some specific entities. I'm going to zoom in, and I'm going to select this coupling to hide, this beam, and this coupling to hide, and also this one, this one. And by the way, the selection mode here is property ID. And then after doing that, I'm going to click here again in invert. And now I have everything that was not visible, which is these couplings and beams. Okay, now I'm going to open up model browser again. And then to assign all these entities to some specific parts, we should click here in set part. Set part, and then select everything, middle mouse button, and then double click on connection entities. Now we have assigned all these entities to connection entities part. Okay. Now click on all to show all. And if I go to model browser and right click on connection entities and show only, I have only these connections. Close, show all. And now we are finished creating these connections. And well, let me see one thing here. Okay, let's just do one additional thing before we finish this video. I wanted to finish the setup of the materials related to the plates. Click in material to see the list of materials, and in here we have these two materials that we need to finish the setup. Double click on this first one, is still for thickness less than 16. Let's check here these properties. So yield strength and elastic modulus are still thicker than, so this one is for less than, so it's thinner than, which is here. Plates thinner than 16, so the yield strength is 391, and the modulus of elasticity is this value. So the modulus of elasticity is correct. Poisson's ratio is 0.3, it is correct. You see that I have an isotropic material. We have the density, correct. Now we need to simply define the plasticity. So here in plastic, select yes, isotropic hardening, because this is a monotonic loading condition. Question mark in the data table, we have this table that we have created for the bolt material, but we are not going to use it. Remember that in here he told us that, let me see here where he talks about it. I don't remember where he talks about it, but he's going to use a perfectly plastic material, which means that, let me create this drawing here so we understand well about it. Stress and strain. And then he says that yield strength is equal to 391, right? So 391. This is the yield strength of this material. And then we are going to have some elastic strain here. We have a straight line. This is the elastic region. The tangent here is the modulus of elasticity. He has defined it as this value, 190707 MPa. And then since this is a perfectly plastic material, the plastic region is a horizontal line like this. So we don't have a strain hardening, which means that we have an increase of strain without any increase in stress. So the material point that reaches this condition loses all its stiffness. All right, so let's define this in ANSA. Let's create a new table, new data table. Let's name it as, this is for thinner than 16. So plastic thinner than 16 mm. Select here, Control A, delete. And then in yield stress, we define 391. Plastic strain 0. So we are defining this point. We are defining this point here. You see, for this point, we have some strain, but this is elastic strain. Here, plastic strain is equal to 0. Oh, sorry. Plastic strain is equal to 0. So that's why we define this as 0, because here we have plastic strain. And then the second point that we can create is, well, the stress is going to be 391, and we can define a value for strain here, such as 0.1. It doesn't really matter. In the plot tab, in axis data, let's invert it. So in here put 2, and in here put 1. Now we have it in the correct, not in the correct manner, but in the way that we are used to. In the y-axis we have stress, in the x-axis we have strain. So you see that we have a stress of 391 here and also here. So we have this horizontal line. Why the plastic strain here is not important, this one that we have defined as 0.1, because what we need to tell Abaqus is that we have this horizontal line. Okay, if we define here as 0.01, it's going to be the same thing. Now, if I have a plastic strain larger than 0.01, Abaqus is going to extrapolate and it's going to continue as a horizontal line. Okay, so let's define it as 0.1. All right, now go back to properties, click on OK. Now we have this new table, double click, and we have it selected here. And that's all we need to set up for this material. Click on OK. And now let's go to the still thicker than 16 mm. Double click here. And then let's check. Modulus of elasticity is defined here, 204,227. And then yield strength is 363. So let's define plastic, yes, hardening, isotropic. And by the way, even here we don't select anything. The standard option is isotropic. But I prefer to select manually because then I have more control over what I'm doing. And then question mark here, and then let's actually get this table that we have just created, right click, or actually select it and click on copy. Now we have a copy, this one with ID 3, and let's, let me see, let's click on edit. And then in here, instead of 391 is 363. And also here, 363. And then this is for plates thicker than 16. Click on OK. And then double click here. And here we have the ID of the table. And that's all we need. Click on OK. And the materials are ready. Now let's save this module. And in the next video, we continue. Well, this tutorial is going to be larger than I thought. It takes a long time for me to explain the things because I don't really want to rush. I want to explain everything so you understand everything that is happening here. Okay. So in the next video, we are going to define contact. We are going to define the loads, boundary conditions, definition of step, and everything else. And also, I guess I'm going to already explain to you how to create the translator so that we can run this model with bolt pretension. I'm not sure if it's going to be worth it to run it like this, because then this tutorial is going to get too long. I'm going to think about what I'm going to do. All right, so don't forget to save, and see you in the next video.